The graph shown to the right represents the force applied by a spring as a function of its stretch. 5 data points were taken on the plotted diagram. Draw a best fit line to the data and answer the following 2 questions. Yes! Yes, yes, yes. We get to draw a best fit line. Free points don't come easier than that, you would think. So that means we are going to get at least a point for drawing a best fit line. So we are going to look at these 5 points. Does it seem like they're pretty much straight in a line? Yes. So then in that case, our best fit line will be in a straight line. Please make sure your best fit line is exactly one line. It's not a little sketch where you're doing one of these things. No, that's bad news. That's not a best fit line. It has to be just one line like that. You may use a ruler on the AP exam. If you don't have a ruler, you can also take your page, fold it over, and then make a straight line that way. Please do that. Don't mess up those free points. Now, is it allowed if these dots look differently? Can you have a curved line of best fit? Definitely. And don't let that stop you. All right, so what is the spring constant for the spring? I don't know. Well, we got a force versus stretch. Rule number 1, when given a graph, look at your axes. What are you given? So we have force, and we're talking spring. So let's see. F equals negative kx. Okay. K equals F over negative x. But that is really with a force because it's a restorative force, so it's always going in the opposite direction. K equals F over x. Fraction and a graph. Fraction, graph. Fraction, graph. Rise over run. So what is K? The slope. And if you calculate this, you can do the rise is 250 over the run is 0.5. So K equals 500 newtons per meter. How much work is done in stretching the spring from 0.3 to 0.5? Work equals force times displacement. Okay? So we're going from 0.3 here to 0.5 here. Here to here. From here to here. Force times displacement. Graph, multiply. Graph, multiply. Graph, multiply. This multiplied by this. This multiplied by this. That's the area under the curve. From 0.3 to 0.5. Take that area, whatever that is. I don't know what the equation is for that shape, but I know what the equation is for that shape and that shape, right? Work it out. I got work equals 40 joules. 1/2 base times height, length times width. So add those together. Suppose a 5 kilogram object stretches the spring 0.4 meters horizontally. The spring launches the object as the spring returns to its natural strength. How fast will the object go upon being launched? Ooh, we're talking about springs and we're talking about how fast? Conservation of energy. Conservation of energy. Let's see, what kind of energy do we have in the beginning? We would have spring potential. Being launched as a projectile, so there's going to be gravitational potential too. In the end, no more spring potential energy, it's natural length. So then we have kinetic energy plus gravitational potential energy. Those two are the same exact because it's being horizontally launched. So we can cancel out gravitational potential from each side. We get 1/2 kx squared equals 1/2 mv squared. Solving for v. Fractions on each side, they go away. We get v equals the square root of kx squared over m. Plugging in our numbers, we get v equals 4 meters per second. 16 before the square root. Check yourself. Can you do that? By now, if you've made it to video number 16 or whatever episode we're on, you need to know how to do this.